is Our next speaker is Peter Carlson. He's coming to us from the University of Minnesota at Twin Cities, where he's primarily doing a lot of computational work. But here in our lab, he wanted to get more experience with experimental things. So he helped me with my project on investigating methylammonium lead bromide perovskite nanocrystals and how those nucleate and grow. And we measured those in situ using different spectroscopy techniques. So yeah, Peter learned a lot of experimental skills, and all of the data he has to show to you today is amazing data that he collected with me. And yeah, he'll start talking when his presentation's up.
Awesome. Okay. All right. Can everyone hear me? Everything good? Awesome. Okay. So thank you, Layla, for the introduction. So, perfect. Okay. So, there we go. Okay. So, as Layla mentioned, a perovskite is a particular kind of material that we see in nature. It's defined by its crystal structure, ABX3, where A is an organic cation, B is a metal cation, and X is a halide anion. Now, the ones we've been particularly interested in are these methylammonium lead bromide perovskites, where in the center of the lattice here, in green, is our methylammonium cation, in black are our lead cations, and in blue are our bromide anions. Now, perovskites are really interesting for a variety of reasons. One such is that they are solution processable, which often translates to scalability and low manufacturing costs. But of particular interest to us are their unique optoelectronic properties, which make them ideal candidates for solar cells and light-emitting diodes. So let's dig more into these optoelectronic properties. We see two major quantum effects that influence the fluorescence of our nanocrystals. First is quantum confinement, where as our nanocrystals get smaller, this changes their electronic structure, widening their band gap. Now, because energy is inversely proportional to wavelength, we see a decrease in the wavelength signal associated with absorption and emission. This is something that we see experimentally. Here in blue at the top there, we see that methylammonium lead bromide nanocrystals with a diameter of 3 nanometers typically absorb and fluoresce at around 450 nanometers. But if we are to increase their size a little bit to 5 nanometers, we see that they absorb and emit at around 500 nanometers. We cap our nanocrystals with organic ligands, which we use to stunt their growth and to keep them quantum confined. Now, digging into this next quantum effect, if we were to take these two nanocrystals, one well capped with these organic ligands and one poorly capped, you can see that bald spot at the top there. If we are to photoexcite an electron on each of these nanocrystals from this lower energy valence band to that higher energy conduction band, this photoexcited electron will assume a new bound state called an exciton. Now, this exciton is allowed to delocalize throughout the entire nanocrystal. And if we take this well-capped nanocrystal, for example, although this exciton is fully delocalized, eventually it will recombine, and this results in fluorescence at some energy greater than or equal to the band gap. But with this poorly capped nanocrystal, eventually these charge carriers will separate, and this positively charged hole will localize on that bald spot, which we call a surface trap. Now, the sort of problem with being localized on this surface trap is that now our charge carriers cannot recombine. This means that our poorly capped nanocrystals do not fluoresce and do not show up in our fluorescence measurements. So what we have been specifically interested in this summer is to characterize that mechanism of methylammonium lead bromide nanocrystal nucleation and growth. So previous research in the Wong group has been concerned with a very similar goal, except with methylammonium lead iodide nanocrystals. And those grad students developed 3 distinct mechanisms that they believe nanocrystal growth could follow, and this is transferable to our bromide nanocrystals. So in mechanism number 1, we see nucleation occur, and then rapidly after nucleation, our nanocrystals become well passivated by those organic ligands, and they stay that way throughout growth. And then in mechanism 2, nucleation occurs, but kind of the opposite happens, where our nanocrystals start poorly passivated, they stay poorly passivated until they reach a point called the surface ligation stage, where our nanocrystals become rapidly well passivated. And now in mechanism 3, nucleation again occurs, and these nanocrystals also start out poorly passivated, but over time they aggregate to form larger, well-capped nanocrystals. Now, our mechanism for nucleation can follow 2 distinct pathways. First is homogeneous nucleation, where nucleation occurs in our solution away from any kind of surface. Now, in this graphic, we see nucleation occur in the bottom left there between that negatively charged green particle and that positively charged red particle. And we can also see in blue is our growing nanocrystal nucleus, and we can see how the partial charge of the surface affects its growth. And then in heterogeneous nucleation, our nucleation occurs on some kind of polar surface or substrate. In this graphic, we can see nucleation about to occur with that positively charged red particle on the polar surface. And again, in blue is our nucleus. Oh, sorry. So what we want as we investigate these mechanisms is some kind of synthesis that is slow enough to measure the growth of our nanocrystals, but long enough to use some kind of in situ spectroscopy. So the synthesis that we use here in the Wong lab is this ligand-mediated transport synthesis. It was developed by researchers at the University of Chicago in 2017, and it's really great for us because it occurs under ambient conditions, and it utilizes this toluene nonpolar solvent. What's also great is that it occurs over 3 hours, but I'm going to get into that in just a second. So we start with our nonpolar toluene solution, and in it are our octylamine and oleic acid capping ligands. We then add our precursors, lead bromide and methylammonium bromide. And what we believe happens next in the reaction mixture is that the organic capping ligands create a partial charge with the lead bromide salt, thereby potentially inducing nucleation. We sonicate this reaction mixture over the course of 3 hours. And then at the end, what we believe to be in solution are some larger, well-capped nanocrystals, maybe some smaller, poorly capped nanocrystals, and then some remaining precursor and organic ligand in solution. Finally, what we can do next is we can filter this reaction mixture to learn more about what is going on and to halt the reaction from continuing. Okay, so Layla and I then decided to move forward with UV-vis spectroscopy on a home-built instrument. Now, the purpose of this initial investigation was to learn more about the nucleation mechanism. We hypothesized that by adding more glass beads into the reaction mixture, which have a polar surface, we might get some insight as to what that nucleation mechanism is. If we see an increase in that absorbance, that tells us that there are more nanocrystals in solution. Thereby, our perovskites very much prefer this heterogeneous nucleation mechanism. We also decided to use this PTFE or Teflon filter. It's really great at filtering precursors out of solution and does not select for the passivity or how well our nanocrystals are passivated by these organic ligands. So we start with this zero bead synthesis. We can see a pretty distinct population of larger nanocrystals at around 525 nanometers. And we see another significant population of small nanocrystals at 450 nanometers. Now, when we add 10 beads, which is the same as adding 1.26 centimeters squared of surface area in contact with our reaction mixture, we see a pretty significant increase in the absorbance with a similar fluorescence. And then when we add 20 beads, we see another significant jump in the absorbance with a similar fluorescence. This tells us that our perovskites definitely prefer a heterogeneous nucleation mechanism, where they like these polar glass bead surfaces to nucleate on. But what's also really interesting is that our fluorescence stays the same. That's kind of unintuitive, right? We have this reaction mixture that's full of these newer nanocrystals, but our fluorescence measurements also do not increase in intensity. This tells us that this newer population of nanocrystals in solution might be poorly capped, because our poorly capped nanocrystals don't show up in fluorescence. So looking at this like strange discrepancy, we can move forward with our in situ spectroscopy to learn more about this interesting population. So I have shown here a traditional transient absorption spectroscopy. In yellow is our sample, and in blue is our pump pulse, which we use to excite the electrons in our sample, and in gray is our probe pulse, which we use to probe the excited state population of our sample in terms of a differential optical density. So at this first time point, we see the probe come in before the pulse, which means we are probing that excited state population before the pump even has a chance to excite it. So of course, our excited state population is 0. Now at the second time point, we see the pump and the probe overlap one another. This means we are probing the excited state population right as the pump is exciting it. So of course, we get the largest excited state population. We call this time point time 0. Now, as the time delay between the pump pulse and the probe pulse increase, we observe this transient decay in the excited state population. Now, traditional transient absorption spectroscopy is really great for a variety of reasons. But unfortunately, achieving good signal to noise is a process that takes around 1 hour. And that is not feasible within the scale of our ligand-mediated transport synthesis, which is 3 hours long. So instead, in the Wong lab, the bread and butter of the Wong lab is this novel method called single-shot transient absorption spectroscopy, where our pump pulse and our probe pulse are focused to align. The pump pulse comes in at an angle relative to the probe pulse and our entire sample, which allows us to spatially encode for that time delay. This gives us the entire excited state decay feature in a single shot. What's great about SSTA is that it allows us to achieve good signal to noise in about a minute, as opposed to the hour for traditional transient absorption. This makes it really great within the scale of our synthesis. So then Layla and I decided to move forward with some SSTA measurements. First, we did a 10-bead synthesis and a 20-bead synthesis. And here I've recorded the SSTA plots at 30 minutes, 60 minutes, and 180 minutes. So looking at this preliminarily, we see this blue feature at around 520 nanometers, and it increases in intensity as the reaction progresses. This is a ground state bleach feature. And if we were to take slices of the time delay between 40 and 45 picoseconds and then average them, we observe these plots. And another thing we can see is that our ground state bleach feature increases in intensity as we add more beads. So previous research in the Wong group has done very similar research with methylammonium lead iodide nanocrystals, and they attribute this similar bleach feature to the presence of poorly capped nanocrystals at a much later stage in the synthesis. What's also really interesting about this 20 beads plot is that small positive feature on the left side. We only see this in the 120 minutes and 180 minutes time point. We attribute this to something called the Stark effect, where if we do have this large population of poorly capped nanocrystals in solution, right, we have established that these poorly capped nanocrystals display a separation of charge with that hole and that delocalized electron. This separation of charge then creates an electric field. And when we have a large population of these poorly capped nanocrystals, we have many different electric fields interacting with one another, and this changes our optical density. So some future directions we can take with this work. We can continue to investigate the derivative features with SSTA, right? SSTA, derivative features, sorry, reveal to us information about the dielectric environment of our reaction mixture. And then we can also further explore bandgap tuning with mixed halide nanocrystals. We've observed that in pure halide nanocrystals, tuning their band gap is very difficult because it's very difficult to get many nanocrystals of a similar size in solution. So instead, by controlling the concentration of bromide and iodide anions in our perovskite lattice, it's much easier to tune their band gaps. But this introduces a set of really interesting chemical problems itself. We also plan to use microscopy to investigate the crystal structure of our perovskite nanocrystals. And I think it'd be really interesting to do some kind of computational study of the nanocrystal surface so we can investigate more of its chemical properties. All right. I'd like to thank my PI, Cathy Wong, the grad students in the Wong Lab, Layla and Zach, and the undergrads, Logan, Anya, and Nick. I'd also like to thank my REU cohort and Priscilla Lewis, and of course, the National Science Foundation, the University of Oregon, and OMQ. All right. Yeah. How do we normalize it? That's something we just do in the code. In Python, we can find the largest fluorescence feature, and then we just normalize it to that. And we only would normalize it to our largest fluorescence data out of all of the syntheses. Oh, Sam? I definitely think it's at least some combination of them. With this data, we don't really know what the mechanism is yet, but I know with the methylammonium lead iodide nanocrystals, we see very much the third mechanism where we have these poorly passivated nanocrystals that then aggravate to form larger ones. And this is also due to something called Ostwald ripening. Yeah, so when we have our sample and we, here, let me open the SSTA. Okay, so when we first excite it with the pump pulse, then we have an excited state population and then a ground state population. And then when we come in with our probe pulse, this probe pulse can interact with this population in any number of ways. And what our ground state bleach feature just indicates to us is that it's difficult to praise. I have a slide for it here. Let me just open it real quick. So in this ground state bleach feature, our probe pulse comes in at the top, and we excite remaining electrons in the ground state. And we see that as evidence of the believed particles in the ground state. Awesome.